Hello everyone, my name is Sheng. Currently, I'm an assistant professor of computer science at the University of Georgia. Now, I'd like to introduce the background and challenges in causal inference. For causal inference from observation data, there are two major paradigms. The first one is causal graphic models, which use causal graphs to represent the causal relations among a set of variables. In this example of causal graph, there are 7 variables, x1, x2, until x6, and y. Each node here is a variable, and each edge represents the relationship between a pair of variables. x1 is connected to y, meaning that y will respond to any changes of x1. In other words, x1 is a direct cause of y. By using causal graphs, it's possible to define some probabilistic models to infer causal effects on the graph. This approach is also relevant to structural equation modeling, ACM, which has been widely studied in social and behavioral science. The second paradigm is potential outcome framework, which is an approach to the statistical analysis of cause and effect based on the potential outcomes. This framework is also known as Rubin causal model or Niemann-Rubin causal model. In our tutorial, we will focus on the potential outcome framework. To understand the idea of potential outcome framework, we need to define some essential concepts. The first concept is unit. A unit is an atomic research object in the causal inference study. It could be a single object, such as a patient, or it could be a collection of objects, such as a group of students. The second concept is treatment, which is an action that applies to a unit. In the binary treatment case, we can define treatment as either 0 or 1. Therefore, we have a treated group which contains all units who receive the treatment 1, and meanwhile, we have a control group which contains all units receive treatment W equals to 0. And of course, we can define multiple treatments according to different applications. The next concept is potential outcome. For each unit treatment pair, the outcome of that treatment when applied on that unit is the potential outcome. There are two types of potential outcomes in general. The first one is observed outcome, which is the outcome of treatment that is actually applied. So we also call it factual outcome because this one can be observed in your data. It can be found in your observation data. The second one is counterfactual outcome, which is the potential outcome of the treatments that the unit had not taken. So a unit can only take one treatment at a time. Therefore, counterfactual outcomes that are always missing, they cannot observed in your data. In causal inference, a major research challenge is how to infer the missing counterfactors. Then based on the definitions of observed outcome and counterfactual outcome, we can define the treatment effects at different levels, including the population level, treated group level, subgroup level, and individual level. At the population level, we can define the average treatment effect, ATE. This equation shows the definition of ATE for the binary treatment case. So we have W equals to 1 and W equals to 0. Y denotes the outcome. In some applications, we mainly focus on the treatment effect on the treated group. So we have the definition of ATT. As you can see, the major difference between ATT and ATE is that in ATT, we have the condition of W equals to 1. So the first term of ATT calculation is observed because the condition here matches. However, for the second term, which is always missing, which corresponds to the counterfactual outcomes. I also want to mention that the definition of ITE, individual treatment effect, might be helpful for some personalized services, such as precision medicine, because this definition can be used to understand the treatment effect on a single subject. Okay, now I want to introduce one example to help you understand the idea of different concepts we have defined so far. Given such a task, we want to evaluate the treatment effects of several different medications for one disease by exploiting the observational data, such as the EHR data. For this task, we may have the observational data, which include the demographic information of patients, some specific medication with a dosage taken by patients, and also the outcome of medical tests. In this task, the units are patients, and treatments are different medications that can be applied to the patients. And the outcome could be recovery status of patients or blood test results or many other medical tests. The success of potential outcome framework heavily relies on several important assumptions. So here I want to introduce three major assumptions for this framework. The first assumption is called stable unit treatment value assumption, SUTVA. The potential outcomes for any unit do not vary with the treatment assigned to other units. And for each unit, there are no different forms or versions of each treatment level, which lead to different potential outcomes. So from this assumption, we can know that first, it assumes that each unit is independent with others. In other words, there are no interactions between units. For example, one patient's outcome will not affect other patients' outcome. There are no interactions. In addition, this assumption also implies that there will be only a single version of each treatment. For example, if one medication has several different dosages, then they should be considered as different treatments according to this assumption. The second assumption is called ignorability. So given the background variable X, the treatment assignment W is independent of the potential outcomes. So this assumption implies that if two patients they have the same background variable X, their potential outcome should be the same, whatever the treatment assignment will be. And if the patients have the same background variable value, we assume that the treatment assignment mechanism should be the same, whatever the value of potential outcome they have. So this is also a very important assumption for the potential outcome framework. The third one is positivity. For any set of values of X, the treatment assignment is not deterministic. The reason is that if the treatment assignment is deterministic, the outcomes of at least one treatment could never be observed, and then it's meaningless to estimate causal effects. This assumption also implies the common support or overlap of the treated and control groups. And if we combine the second assumption with the third assumption together, we also call them strong ignorability or strongly ignorable treatment assignment. So given the definition of potential outcome framework and given the task of treatment effect estimation, we may think about some potential solutions to this problem. The core problem in causal inference is how to estimate the average potential treated or control outcome over a specific group. One naive solution is to simply calculate the difference between the average treated and the control outcomes. Such as this equation, we can estimate the ATE by using the difference between the outcome in treated group and the control group. So NT here denotes the number of samples in the treated group. NC means the number of samples in the control group. YI and YJ denote the outcomes in each group. However, this solution is not reasonable due to the existence of confounders. So what are confounders? Confounders are variables that affect both treatment assignment and also the outcome. Let's take one example to understand the idea of confounders. In our medical example we just mentioned, age might be a confounder because age would affect the recovery rate and age would also affect the treatment choice. Let's look at one table to understand the idea of confounder by using age as one example. In this table, we have different age groups, young and older, and we have two treatments. They could be two different medications, treatment A and treatment B. If you look at the overall treatment effect, you can see by using treatment A, the recovery rate will be 83%. By using treatment B, the overall recovery rate will be 78%. So you may conclude that treatment A is more effective than treatment B. However, if you look at the different age groups in detail, there are some interesting observations. If you check the results for young group only, you will see that, okay, for the young group, treatment B is actually more effective because the recovery rate is much higher. And meanwhile, for the older group, we have the same conclusion. Treatment B is more effective. So this kind of analysis will give us quite confusing results. This is also called Simpson paradox due to the confounder. So the confounder will also lead to the issue with selection bias because the distribution of observed group is not representative to the group we are interested in. In this example, you can see young people, they are more likely to receive treatment A because there are 270 young patients who receive treatment A. However, only 87 received the treatment B. On the other hand, more older people, they tend to receive treatment B over treatment A. Therefore, as you can see from the histogram here, different age groups, they have different preference of receiving treatments. So this is the issue of selection bias, which will make the counterfactual outcome estimation more difficult. Okay, a quick discussion for the background and challenges in causal inference. We mainly discussed the definition of potential outcome framework, and we discussed the definition of units, treatments, potential outcomes, factual outcomes, counterfactual outcomes, and the different definition of treatment effects at different levels. We also noticed that a naive solution for treatment effect estimation will not be reasonable because of the existence of confounders. Then the main challenges in causal inference from observation data is how to handle confounders, and meanwhile, how to deal with selection bias. Next, Zheyan will introduce some traditional approaches for causal inference from observation data.